Great. Okay. So hello, everyone. Thank you for attending another one of our machine learning lunch seminars. Today, we are excited to host Professor Ziv Goldfeld. Ziv is an assistant professor in the School of Electrical and Computer Engineering and a graduate field member in computer science, statistics, data science, and the Center of Applied Mathematics at Cornell University. Before joining Cornell, Ziv was a postdoctoral research fellow in Leeds at MIT. Ziv graduated with bachelor's, master's, and PhD in electrical and computer engineering from Ben Gurion University in Israel. And Ziv's research interests include optimal transport theory, statistical learning theory, information theory, and mathematical statistics. Ziv's honors include the NSF Career Award, the IBM University Award, and the Rothschild Postdoctoral Fellowship. So with that, Ziv, the stage is yours.
All right, thank you, Sohail, for the very kind introduction. It's a real pleasure to be here, hopefully next time in person. But yeah, I'm really glad to speak at the seminar. Now, today, I'd like to talk a little bit about optimal transport theory, which is a powerful, I would say, framework for measuring discrepancy or just simply comparing probability distributions that recently became very popular for a bunch of different applications, from statistical inference and machine learning to biology and economics. And I mean, it's really broadly applied nowadays, though the problem with optimal transport distances is that they suffer from statistical and computational hardness issues in high dimensional settings, which basically makes coupling these applications with meaningful formal guarantees essentially impossible, especially given, like, if you keep in mind just how high dimensional real world data is nowadays. And that's a major issue. And this sliced optimal transport framework, which is the topic of today's talk, gives us essentially a way around the statistical and computational hardness by projecting the problem down into a lower dimensional space. And what I'll try to show you today is that despite this projection process, sliced optimal transport, on one hand, kind of maintains a lot of the structure of the virtuous, I would say, structure of classic optimal transport, while being more amenable for efficient computation estimation. I'll present some recent theoretical advancements that we had on the topic. And with that, I mean, I'd like to get started, but please do feel free to stop me with questions on the fly. I'm happy to take those, and so that everybody's on the same page throughout this presentation. All right. Yeah. And getting into things, I mean, the motivation for optimal transport, and more generally for discrepancy measures between probabilities, which we generally call statistical divergences, and I think at least it's a good motivation for this crowd, really comes from the fact that many machine learning tasks can be cast as either comparing or transforming high dimensional probability distribution. So in a sense, there's like a picture like this at the background of all these examples. And for some of them, you may want to learn a transformation or interpolation between two given distributions, like in the case of style transfer. In some other ones, you might want to approximate some target distribution by a model under a certain divergence, which is essentially what you're doing in generative modeling. But the point is that by formulating our task in terms of a statistical divergence gives us a clean mathematical problem that lends well for analysis. And you can now study this problem in order to try and, I mean, understand the task better, derive formal guarantees, and generally like obtain a theory for this task that you're performing. And maybe to give you a better sense, let me show you how this formalism works for this generative modeling example. All right. So generative modeling, and the goal here is to fit a parametrized model mu theta to some underlying data distribution mu. And one way for doing that, which is quite popular in practice nowadays, is the so-called implicit or latent variable generative modeling approach, which produces this learned mu theta by starting from some simple latent random variable z that lives in a much lower dimensional space, and then pushing it through some potentially randomized parametrized mapping to kind of expand it to the space where the data resides. And if we describe this transformation by this conditional distribution u sub x given z sub theta over here, then the generative model we're getting out of this process is simply the induced marginal distribution on the X space, which is obviously given by this marginalization formula. And this is how this thing looks like in a picture. So you have your latent variable over here, you push it through your transformation to obtain this red blob in the target space that represents the generative model. Tweaking the parameters of the transformation changes the blob, and your goal now is to match it or make it as similar as possible to this blue blob, which stands for the data distribution. And that's kind of the high level idea. But you can imagine that in order to study such a problem, the very first thing you need is kind of a means to quantify this desired proximity between the model and the data distribution. This is exactly where divergences come into play, because by now, I think it's almost standard to formulate generative modeling questions under the so-called minimum distance estimation framework, where you basically pick your favorite statistical divergence and then infimize over model parameters this divergence between the data distribution and the model that we're trying to learn, right? So does this make sense? Yeah. And I mean, it turns out that there's actually quite a lot that you can say and deduce about generative model using this minimum distance estimation framework. For example, you can analyze generalization errors and stuff like that. And like I said, provide formal guarantees. And while, of course, there are many different divergences to choose from, today we're going to focus on this very interesting and special class of optimal transport distances. So, I mean, next thing I want to do is set those up, unless there's any questions about this idea. All right. Yeah, so optimal transport. And I think that the basic idea here is very nicely illustrated by this picture over here, where you can think of transforming a fixed amount of mass from one shape into another, say sand into a castle, in the most cost-efficient way with respect to some given cost function. And to formulate this, our piles of sand are modeled by two probability distributions, mu and nu. So mass is kind of normalized to 1, which doesn't really matter, of course. And we are given this cost function C over here that represents perhaps the price or maybe the effort in transporting a unit of mass from a point X in the support of mu to a point Y in the support of nu. And, perhaps kind of the first natural way to go about this reshaping is just to look for a function, to look for a deterministic transformation. And maybe to explain that, let me move to a slightly more schematic illustration. So given our two distributions, we want a function that would rearrange the mass of mu into that of nu. In this simple situation over here, obviously just the translation would do the trick. And by the way, if you're not familiar with this notation over here, this is the so-called push forward measure that just represents the distribution of a function of a random variable. So if X is distributed according to mu, then T of X is distributed according to the T push forward mu. All right, that's just this push forward notation. And from this equality over here, you see that this is really the requirement. We want a function that would reshape mu into nu. All right. And such functions is what we call transport maps. And this is really kind of brings us to the original formulation of the optimal transport problem, which is due to Gaspard Monge from almost 250 years ago, where we essentially look at the most cost-efficient way of transporting mu onto nu, where we optimize over all such deterministic transportation strategies as modeled by these transport map functions that we have just introduced. All right, does this make sense? Any questions here? Okay. But, while I think this makes kind of perfect intuitive sense and is a very sensible way to set up the problem, it turns out that as a mathematical formulation, this Monge problem actually has a bunch of issues. For example, the set of transport maps may be empty. A transport map between two distributions may not exist. And let me say that this is a highly non-pathological statement. I mean, there are simple examples of distributions between which we cannot find a deterministic transportation map. And just think of this situation where you want to transport a point mass into kind of a half-half distribution on 2 points, right? What does T do to X? Does it take it to Y1 or to Y2? I mean, you cannot do both, right? It's just a function, just a deterministic function. You cannot split the mass and send half here and half there. Again, just a function. And indeed, in this simple example, we don't have a transport map, and the problem is ill-defined. We're infimizing over an empty set. But even when optimal transport maps do exist, it turns out that this set of maps is actually not closed under any reasonable topology. So again, this infim has issues. Does it ever achieved? really unclear. And beyond all of that, if you think of this problem in terms of this t, which is essentially the optimization variable, you see the problem is highly nonlinear, which makes it quite hard to work with, quite hard to analyze. And therefore, I mean, the Munch formulation kind of, Munch had the right idea, but not quite the right mathematical formalism. And it turns out that this inability to split mass is really the core issue of the Munch problem. And this issue was fixed almost 200 years later by Kantorovich using the notion of couplings. So let me denote by this cap pi of mu nu over here, the set of all couplings of my two distributions, where a coupling is just a joint probability distribution on the product space that has mu and nu as its corresponding marginals. And really, I mean, you can think about couplings just as randomized mapping. This is what they model, now allowing us to split mass. And with that, the Kantorovich problem is just the following thing. I mean, the exact same idea as before, just with transport maps replaced by couplings. So again, the most cost-efficient way of transporting one distribution onto another, now infamized over randomized transportation strategies as captured by this coupling set. All right? Any questions about this? Okay. So I'd like to mention maybe a couple of things about this Kantorovich problem. First of all, one should note that it subsumes the Munch formulation as a special case under certain regularity conditions. If there is indeed a map that transports mu onto nu, the Kantorovich problem will be able to retrieve that. So the optimal coupling will be induced by a mapping. But perhaps even more importantly, notice that the Kantorovich formulation lends us at an optimization objective that is linear in pi, which is optimized over the set of couplings, which is defined by constraints that are linear in pi. I mean, these are just integrals. So all in all, what you arrive at here is an infinite dimensional linear program. Now, infinite dimensional on one hand, but linear program nonetheless. And this carries a lot of benefits and a lot of structure that I will discuss shortly. But like I said, I mean, this is kind of today the canonical standard way to set up the optimal transport problem. And perhaps the most kind of popular instance of this Kantorovich optimal transport is the situation of the so-called Wasserstein metric, which is obtained from the Kantorovich problem just by taking your cost as the pth power of a metric, which in this talk I'll just canonically assume is the Euclidean distance, and then taking a pth root of the entire thing. So this is how we define Wasserstein distance through the Kantorovich optimal transport problem. And the reason why we like Wasserstein distances is that because they possess some really, excellent properties and carry a lot of structure, which I would like to explain next. But if there's any questions about definition, like I said, I mean, just feel free to stop me. And the first thing I want to mention about Wasserstein distances is that, in fact, they define a metric on the space of probability measures with finite pth moments. So this subscript p over here just denotes that I'm restricting attention to distributions that have a finite pth absolute moment. And this pair over here, the space endowed with the metric, is what we typically call the Wasserstein space, which turns out to be a very interesting object, very interesting and structured space to think about, because, for example, this WP metric, in fact, metrizes the topology of weak convergence, which is important for various reasons that I won't get into in this talk. And moreover, and I think this is actually an interesting thing to be aware of, it turns out to induce quite a rich geometry on this space of distributions, which is in many ways very similar to the Euclidean geometry. And what this allows us to do is to lift ideas in intuition from the Euclidean case, which we understand very well, in order to analyze this very abstract space of probability distribution. So there's a lot of virtue in this geometric structure of that Wasserstein space. Now, that's one. But maybe from a slightly more kind of pragmatic standpoint, Wasserstein distances, that's another important property, also enjoy robustness to support mismatch, which means that WP between mu and nu will give us a finite number that is a meaningful notion of distance between these distributions, irregardless of whether their supports are aligned or disjoint or kind of somewhere in between. And this is important for applications because, for instance, if you think about generative modeling again, then you can imagine that at least at the beginning of the training process or your optimization process, the data distribution and your model have very little to do with one another, let alone having the same support. right? And you don't want your distance to misbehave in these situations, explode to infinity, or become vacuous in some sense. So we want this robustness, and the Wasserstein framework gives us that as well. And last thing that I want to mention at this point is that Wasserstein distances, and more generally, in fact, Kantorovich optimal transport, by virtue of being a linear program, enjoys a strong duality theory. And for example, in the case of p equals 1, the one Wasserstein distance can be written as this supremum over Lipschitz 1 functions of this so-called discrimination difference. This is just the difference of expected values of the function phi one time with respect to mu minus its expectation with respect to nu. And this formula over here that is sometimes called the Kantorovich-Rubinstein dual form is actually very, very helpful for computation. And in fact, it's kind of the basic idea behind Wasserstein generative adversarial networks, WGANs, because I mean, the WGAN really almost immediately falls out from the minimum distance estimation problem with the W1 cost when you plug in this Kantorovich-Rubinstein dual form. And I think it's a very cool connection to be aware of. So let me maybe show you how this happens. All right. So I'm just rewriting my Kantorovich-Rubinstein dual over here in expectation notation. And to arrive at my Wasserstein GAN, all I really have to do is some recasting here, okay? So let's think of mu in blue over here as my data distribution, making X a data sample, all right? Let nu be my generative model nu theta, which in the case of a GAN is typically taken as some deep neural network G sub theta, theta being the parameters operating on some latent variable Z, all right? And lastly, let me parameterize this space of Lipschitz 1 functions by another deep neural network, call it d sub psi, psi being the parameters. Usually this is called the discriminator network or the critic, which is now constrained to satisfy this Lipschitz 1 requirement. And if you now kind of throw this all into a block diagram, you get a system that roughly looks like this. You have your latent variable over here, you push it through your generator to obtain the synthetic, the generated sample at the output. Tweaking the parameters of the generator network changes this distribution. This is the set of nu theta's distribution that we are generating here. Over here on top, I have my real samples. Distribution of these guys is mu. And the job of the discriminator now is basically to tell these two apart by comparing expected values of Lipschitz 1 functions. Now, I mean, having that in practice, you would kind of pit these two neural networks against each other in a minimax game that is evolved via some alternating optimization procedure until you kind of reach an approximate equilibrium, at which point you have a generative model at your disposal, right? I mean, just feed in latent variable values and observe generated samples at the output. But what I would like to emphasize, like I said, is the connection to statistical divergences. And the thing is that if we look back at the minimum distance estimation problem with respect to this W1 cost, and think of what does it mean to infimize over model parameters theta, this W1 distance between mu and nu theta, and plug in this Kantorovich-Rubinstein dual form, we arrive at exactly the minimax GAN formulation that is at the heart of this system and any other GAN architecture out there, which, I mean, I think is kind of cool, like I said, and everything fits together very nicely. Plus, from this connection, we really also get an explanation of what these GAN architectures are actually solving. I mean, this architecture was proposed earlier before the connection to the Wasserstein distance as some very clever heuristic idea, but when the Wasserstein GAN came along, we actually understood that, oh, what this actually being done here is a solution to a minimum distance estimation problem with the one Wasserstein cost, at least when your discriminator function is one Lipschitz. All right, so that's the connection to some state of the art deep learning models. But yeah, the thing is, that in this application, as well as in many others, we don't really know these two distributions. We don't really know mu and nu, right? We don't have the actual population distributions. We only get samples from them, which necessitates estimating optimal transport distances. And perhaps the simplest approach here would be to first estimate my two distributions, say, for example, using these empirical measures that I have over here, and then plug those into WP in order to arrive at this empirical proxy, right? And that's really a good question at this point. I mean, does this empirical Wasserstein distance serve as a good approximation of the population one, which we actually care about? And unfortunately, the answer is that it is far, far from being the case, especially in high dimensional situations. This is exactly what the curse of dimensionality is about. And I mean, by now, it's kind of classic result at this point that dates back to Dudley from 1969, that the rate at which the empirical Wasserstein distance converges towards the population one is in general given by this n to the minus 1 over d expression over here, with d being the ambient dimensions where my distributions are supported. And I mean, evidently, this is super slow and deteriorates very, very drastically as dimension becomes larger. And I should mention that you cannot really improve upon this rate by doing anything smarter here. For example, like using fancier estimators of the distributions, or maybe avoiding plug-in methods altogether. All of this will buy you at most polylogarithmic factors. And the source of the problem here, and this is the reason why this rate is unavoidable, is because optimal transport distance between a Lebesgue continuous distribution and any discrete distribution on endpoints, in particular these empirical measures, suffers from this n to the minus 1 over d rate almost surely. There is essentially, if you think about where this exponent is coming from, there's a Euclidean covering argument in the background here. And the rate is associated with the cost of transporting d-dimensional Euclidean balls onto discrete set of points, onto their centers, let's say. So this is kind of a fundamental property of the optimal transport problem. It's not a consequence of some bad estimator. This is unavoidable and is a big, big issue because this rate is just way too slow to be able to guarantee anything about anything, again, especially when you think of modern data sets and how high dimensional they may be. So that's the curse of dimensionality. And, beyond being kind of an issue in its own right, turns out that it's also a bottleneck towards a finer statistical analysis that, for example, concerns limit distribution theorems or consistent resampling methods. All of these are largely unavailable for classic optimal transport and are key for valid statistical inference. So, I mean, we want these types of results, but they're nowhere to be found under this classic framework. And beyond that, the statistical hardness also actually reflects on the computational side of things, because when D is large, you need lots of samples. But when you use lots of samples, then the cubic complexity of solving linear programs becomes prohibitive, right? And when n is sufficiently large, then this is an infeasible problem, despite being an LP. So, I mean, all in all, like I said, this curse of dimensionality thing is a major issue of the classic framework and kind of the main thing that we want to try and resolve or tackle in this talk. All right? Any questions up till now? All right. So, I mean, for these reasons, in recent years, what started to happen is we started to see kind of the emergence of very clever ideas so as to kind of how to regularize the original optimal transport framework in order to try and alleviate these statistical and computational issues with the hope of preserving as much of the original structure as possible. And really, the name of the game here is to balance out these three key aspects, where maybe on the structural side, you may want your regularized version to preserve the metric and topological Wasserstein structure. You may want to inherit the duality theory, which is useful for a bunch of applications. And maybe you even want to kind of have a good proxy. You want your regularized OT framework to be a good proxy of the classic one, which is, for example, very useful for proofs. On the computational front, I mean, obviously you want efficient algorithms with complexity guarantees and perhaps even kind of compatibility with modern neural network-based implementations so as to be able to handle large tasks, large high-dimensional tasks. And a duality theory actually kind of gives you that. So that's why duality is important. While on the statistical side of things, well, obviously we want fast empirical convergence rates without curse of dimensionality, and then being slightly even more kind of adventurous, we want limit theorems to better understand the fluctuation of the estimation error. We want consistent resampling methods like the bootstrap, for example, and things of this sort. And I think that, I mean, at this point, there are kind of three key prominent regularization methods for optimal transport that I would like to mention. The first of which is called entropic OT, entropic optimal transport, is probably the most popular one. Its recent popularization goes back to a wonderful 2013 paper by Michael Couturi. And the idea here is really to kind of convexify the original linear problem by introducing this entropic penalty. And turns out that this actually gives you pretty much everything that you want in terms of statistical and computational aspects. I mean, you can compute this thing using the Sinkhorn algorithm, which is very fast and highly parallelizable. And then on the statistical side, you have fast empirical convergence rates. You have a bunch of limit theorems. We know a lot about the statistical behavior of entropic OT. However, on the structural side, it turns out that entropic optimal transport loses almost all of the original structure. I mean, it's not even a metric to begin with. And while you can kind of fix the, easy axioms of a metric by some centering arguments, it will still not be a metric even after those types of fixes. This is called the synchro divergence. So, I mean, all in all, probably in this diagram, I'll place entropic optimal transport probably somewhere here. Does well on computational and statistical side of things, but not so much on the structure. Okay. Next, we have smooth OT, which I've introduced together with some collaborators a few years ago. And the idea here is to take a smooth kernel function, is essentially to convolve it with our two distributions in order to level out local irregularities. And this kind of makes the problem nicer in a very specific sense. And for this smooth framework, turns out that it actually inherits almost all of the classic structure, which is a nice thing, and also has an excellent statistical profile, very similar to the entropic one. But I mean, at this point, we don't have an efficient algorithm for computing it. So it kind of falls short on that front. It probably sits somewhere here in my diagram. And yeah, maybe I should mention that the absence of an algorithm here is not due to lack of effort, right? I mean, this is really comes from the fact that computing smooth optimal transport essentially boils down to computing classic optimal transport between mixture models. And this is a very hard open problem in optimal transport. And this is why, I mean, essentially computing this smooth OT seems non-trivial at this point. Now, for the last but not least regularization method, which is sliced OT, and is our focus today, I'd like to argue that it almost sits nicely in the center here, perhaps up to one structural property in which it's slightly lacking. And at this point, I want to start getting into it and try to explain to you why and how I believe that this is indeed the case. Okay? So let's start from the beginning, which is, of course, the definition. What is sliced optimal transport? Well, I will focus on the case of sliced Wasserstein distances, but everything can be generalized to other cost functions as well if you care about that. And there are essentially two variants that I want to mention: the average and the max sliced Wasserstein distances as defined over here. And in both cases, what we do is take our d-dimensional distributions, our high-dimensional distributions, pick a random projection direction theta from the unit sphere in the corresponding d-dimensional Euclidean space, project our distributions onto that direction in order to, obtain a pair of one-dimensional distributions, these ones over here, right? And then simply take the average, measure the distance between these one-dimensional distributions, and simply take either the average or the maximum over the different choices of theta to obtain the corresponding sliced distance variant. Okay, so that's how we define those sliced distances. You project an average or project and maximize. And the motivation for doing that is that so it turns out that optimal transport between one-dimensional distributions is a simple problem, unlike the d-dimensional case. First of all, I mean, you can generally compute WP between distributions on the real line as the LP norm, computed in closed form as the LP norm between their quantile functions, which further in the p=1 case simplifies to the L1 norm between CDFs. So I mean, no optimization here, closed form expression that's already quite an advancement from the general case. And if beyond that, you're in a discrete situation of two distributions that are supported on n points, then the optimal transport problem in one dimension becomes essentially just an optimal matching problem whose solution boils down to, well, if these are random samples, finding order statistics, or more generally, I mean, just sorting, right? Essentially sorting, which is an easy operation. So all in all, the point here is that computing WP between those projected distributions, which is the integrand over here or the optimization objective over there, this is cheap to do. This is easy. Now, we still need to figure out how to perform the integration or how to perform the optimization. And I'll talk about that in a minute, but it's an excellent starting point. Let's put it like that. All right. So that's the definition. And with that, I mean, at this point, we kind of want to start to understand, okay, what have we gained from this? What have we potentially lost in terms of these three aspects: structure, computation, and statistical? But if there's any questions about definition, I'm happy to take those first. All right. Okay. So let's talk about structure. Let's start from structure. And first of all, and so it turns out that both the average and max slice distance inherit the metric structure of classic WP. And in fact, they generate the exact same Wasserstein topology. This is something that actually appeared in one of Suhail's papers from 2020, but was re-derived later on in 21 as well, I think for the max slice distance here. So, I mean, that's great. You inherit the metric and topological structure. And maybe as a testimony of that, these are some images that are generated by a sliced version of the Wasserstein GAN. And as you can see, I mean, the sliced distance can still capture complex data structures reasonably well. And the reason that these images maybe not look as fancy as some of the other ones available there, I mean, it's mainly kind of a parameterization question, right? I mean, how large is the model you want to be using? And this model, I would say, was rather conservative. But I mean, we can still capture complex data structures using these sliced metrics. So that as far as metric and topological structure. How about duality? Well, it turns out that for the max slice distance, we actually get a very Kantorovich-Rubinstein-like dual form. Say, for the case of p equals 1, if you start from the definition and then plug in the dual form for regular W1 here on the inside, then you can essentially combine the two suprema, the 1 over thetas in the unit sphere and the 1 over Lipschitz functions now on the real line, in order to arrive at a single optimization over the class of 1 Lipschitz functions on R that are now composed with these projection operators. And that's our dual, right? So a slightly different function class, but a dual form nonetheless. And this is quite workable. I mean, in fact, this sliced Wasserstein GAN that I've just mentioned is implemented exactly based on this formula over here. And it's also quite useful for a bunch of proofs that I'll mention later on in this talk. So we also inherit the duality. The one structural aspect where I would say slice distances kind of fall short is really the approximation bit, because you see, I mean, in general, there is an exponential in dimension gap between classic and sliced WP, as for example, is evident by this lemma from Bonote from 2013. And the thing is that there is no, there's no sort of tuning parameter here to make this approximation arbitrarily small, which is something that you often want from a regularized framework, whether to use for proofs or for practical applications. Maybe you're trying to approximate the classic distance. And well, I mean, the point is that you cannot have that under the sliced framework. We have projected the problem down to a lower dimensional space, and there is some inherent information loss in doing that, and it is what it is. So, I mean, you cannot approximate classic distances arbitrarily well using sliced ones, okay? And that's pretty much what I wanted to say about structure. Now, from here, I want to move on to the computational aspect, at which point we basically want to understand how to go about computing the average or the maximum over theta, and what kind of formal guarantees can we expect to get from the corresponding methods. And let me address this question maybe starting from the average sliced case. And for that, first thing I want to do is define just this shorthand, this W of theta function over here, simply as the WP distance between the projected empirical distributions raised to the power of P. And again, first of all, recall that we can easily compute this guy via sorting, and then that the average slice distance itself is nothing but the integral of this function over the unit sphere. All right. And with that, I mean, perhaps, the most natural way to go about computing this integral, and this is again something that was proposed by Suhail and his collaborators in this 2020 paper, is to use numerical integration, to use Monte Carlo integration. Essentially, I mean, you draw a bunch of theta L's uniformly at random from your unit sphere and take one big happy empirical average. And I mean, if I'm not mistaken, I think in this paper, you guys showed that the error of this Monte Carlo estimate scales as the root of 1 over L, the number of Monte Carlo samples, times the variance of this function over here, where theta is uniformly distributed over the sphere, but this variance itself was not actually analyzed. That's right. And we've been able to close this gap in our recent work, and this will appear in the upcoming NeurIPS conference, establishing the following bound on the overall error of the Monte Carlo estimate. And let me first kind of get this second term out of the way. This delta n over here is nothing but the empirical estimation error, essentially the rate at which empirical measures converge to their population limits under slice WP. And I will account for that when we talk about statistical aspects. So let's kind of put this aside for now, because the interesting term here is this first one, which bounds the error due to the Monte Carlo step. And like I said, it corresponds exactly to this variance that I mentioned a moment ago. And so the question is really, how do we analyze this variance? How do we control it in order to arrive at this value? Okay. And well, it turns out that the key step here is to show that this projected distance this W of theta function of mine is in fact Lipschitz continuous in theta. And we also characterize its Lipschitz constant. And this allows us to use concentration arguments of Lipschitz functions over the unit sphere in order to arrive at this variance bound over here. And yeah, maybe one thing that I want to mention about this result is that this log concavity that is assumed in the statement of the theorem about the population distribution is not strictly needed for analyzing the Monte Carlo error. Rather, any exponential concentration of Lipschitz functions would suffice, and log concavity gives you that. But for the analysis of the empirical estimation error, we actually require log concavity, which is why I decided to just state the result in these terms. And I mean, all in all, this is basically how we compute average slice WP subject to formal accuracy guarantees that are given in terms of basic characteristics of the population distributions. There's nothing but means and variances or covariance matrices here. And I think that it's also worth mentioning this inverse dependence on dimension in this first term over here, which shows that while large D makes empirical estimation harder, delta n will grow with D. I will show you this soon. It turns out that large dimension actually helps you in terms of the error that is due to the Monte Carlo step, which I think is an interesting observation. And here's a simple simulation in that regard. I mean, this is just some, isotropic Gaussian setting, but you can note that the Monte Carlo error indeed becomes smaller as dimensions grows, which is consistent with the theory. And that's pretty much what I wanted to say about computing average slice distances, essentially Monte Carlo integration. Now we have strong bounds as far as how accurate these estimators would be. Okay. How about max slicing? Well, I mean, again, turns out that there's a simple and elegant solution here. And for that, I want to rewrite my max slice, my empirical max slice distance in this form over here, mentioning two things. The first is that I've changed my optimization domain from the sphere to the ball, which I can do by a simple rescaling argument. This is helpful because now you're optimizing over a convex domain, right? And second of all, I've thrown in a couple of minuses here in order to arrive at this minimax form where the inner maximization is over permutation. I mean, this is essentially corresponds to sorting being the solution of this problem, whereas the outer minimization is over the different theta projection, the projection directions in our unit ball in this situation. All right, so that's just an equivalent way of expressing this distance. And with that, we can essentially employ what's called projected subgradient methods in order to compute this distance by noting that the subgradient of this inner maximization over here, which I want to denote by W tilde of theta, this subgradient is easy to compute. And why is that? Let's understand why I can easily compute subgradients of this W tilde of theta function. Well, first of all, this function is given as a maximum of a bunch of affine functions, and we know that the subdifferential of such functions is given by the convex hull of all the slopes of all the functions that achieve the maximum, right? I mean, this is kind of basic optimization theory. And the thing is that we can easily find one such optimizing function simply by computing the optimal permutation that corresponds to a specific theta. And having this permutation, you can then easily get the subgradient with respect to theta of this inner row function over here. I mean, just, differentiate this each of these summands with respect to theta and aggregate these gradients in order to get the subgradient of rho at this optimal permutation. And so, I mean, all in all, you have everything that you need in order to compute this max slice WP via an EM-like algorithm where the minimization step is implemented using this projected subgradient method. And again, a version of this approach was proposed by Suhail in this same paper that I've mentioned in the previous slide. But what I'd like to say here is that with this perspective and using the fact that when P equals 2, we can show that this W tilde 2 of theta function is in fact weakly convex in theta, we can once again provide formal guarantees. Essentially, we can run through a local optimality analysis and show convergence to an epsilon approximate local optima in big O of epsilon to the minus 4 steps, which gives the computational complexity of this previously heuristic method. And again, if you numerically kind of compare the simple algorithm to fancier computational methods for max slice WP based on Riemannian optimization, then you see that our approach, or Suhail's approach, to be honest, which is described by this this solid lines over here converges much faster, though. I mean, I should note that the other optimizers that I mentioned can also be adapted to the case when you slice to more than a single dimension, whereas our algorithm is particularized to this one-dimensional setting. All right, so that's as far as computing mass slice distances. And maybe I should also say a word about global optimization here. I mean, if you want to compute the global optimum, you can do that. Essentially using the Lipschitzness of the objective that I mentioned before. There are global optimizers of Lipschitz functions based on function evaluations, and we've also analyzed these in the paper, but the rates that you would get from these would be exponential in dimension. So honestly, I think you're much better off kind of settling for local optimality subject to these fast convergence guarantees. And yeah, I think that's pretty much everything that I wanted to cover about computational aspects. And at this point, I would like to move to the last thing we want to discuss, which is the statistical question concerning slice distances.
So there's a question, if Daniel, yep.
Yeah, so I'm still stuck on this 1/√D factor for convergence. Sorry, convergence. Yes. So does this have something to do with essentially the concentration assumptions, or the log concave assumptions that we've made on the?
Not really. This really comes from the fact that, you know, when you think of these projections, that essentially you sort of summing up a bunch of entries of a random vector, and this averaging turns out to help you as far as the Monte Carlo step. Now, this log concavity does give you a certain control over the variance of this function. I mean, without some concentration of Lipschitz function property in the background, I don't know how to, bound this variance otherwise. So, I mean, the log concavity is used here in that sense, but my interpretation of why D appears here is because when you perform this inner product between theta and your variable, you essentially be looking kind of at a sum of a bunch of entries that somehow introduces an extra averaging effect that helps you in terms of the error associated with the Monte Carlo step.
So the statistical complexity of these entries can't grow in the dimension, then it's somehow fixed.
Sorry, you mean for delta n over here?
Yes.
So that's the next thing. I'll show you how delta n behaves.
Okay.
But this is not the behavior that you'll see for delta of n. The empirical estimation error will, in fact, when it depends on dimension, it depends on it in the inverse sense. Large dimension makes this question, in fact, harder.
Okay. I will try and keep up, and I'll let you keep going. Thank you for.
Yeah, but do chime in again if you want to add anything else. Okay. All right.
One more question.
Yeah.
Ikun, would you like to ask the question?
Yeah, I just have a question. Because I remember in Wade paper, he proved that tropical T sample complexity, he only required the merit to be to be a sub-Gaussian. He extended Coulter result. Coulter result required two merit to be compact. But at here, why we need a stronger? I think log concave is stronger condition than the sub-Gaussian, right? So my question is why at here we need a stronger result.
All right, so let me repeat the question if I understand correctly. So you're talking about entropic optimal transport, and you're saying that, originally we had the sample complexity due to Couturier and friends, which kind of accounted for compactly supported distributions. Then I think it was Gonzalo and Mena and Jonathan Niles-Weed that generalized this to quadratic cost and Gaussian distributions, right? So again, I'm not talking about sample complexity just yet. This is just the error due to this Monte Carlo averaging thing. But when I will talk about sample complexity, I will once again assume log concavity. And you're right that this is a stronger assumption than some of the other regularity assumptions that are imposed in the literature. But what we can get under log concavity, and I'll show you how in just a bit, is faster convergence than any other rate that was available up until now. So, there's obviously a trade-off. More structure, perhaps better results, and that's exactly the structure that we kind of explored. Yeah. Although I should also mention that log concavity is actually not comparable to some other assumptions that are available. They're kind of mutually exclusive in general. So let's talk about statistical aspects, and starting from kind of the first order of business, which is the empirical convergence rate in expectation. And the first thing that I want to say here is that in another paper by Suhail, I mean, he did a lot of work on these slice distances, a lot of excellent work. They actually showed that the convergence rates of average slice distances between high dimensional distributions adapt to the one-dimensional empirical convergence rates under the base measure, under the base divergence, which is already great news because it means that there's no curse of dimensionality in terms of dependence on n, right? Which is kind of maybe the first thing to be concerned about. However, this specific result does not capture possible dependence on dimension of the constant, of the prefactor, which, to be honest, is also important to understand if you want to kind of see how scalable this approach to high dimensional settings, right? And I mean, there were results in that space that did capture dependence on dimension and also, in fact, treated the max slice distance subject to various regularity assumptions, although some of these assumptions are quite high level and may be hard to verify in practice. And what we did, and this is another result from that Europe's paper, is fully characterize the rates under this low concavity assumption, which might be stronger than some of these. For example, low concavity implies Poincaré, right? But on the other hand, low concavity, I view it as a primitive assumption. You show me a distribution, I can immediately say if it's low concave or not, right? It's not some high-level condition that is hard to check. And this is the result that we have, right? And there are probably three things that I want to say here. The first of which is that you can notice that all the constants here are specified in terms of the covariance matrix sigma and the problem's parameters. So I mean, the result is explicit in this sense. Then the rates that we get are in fact faster than any other available in the literature. And for this average sliced case, this rate is in fact sharp. We have a matching lower bound. And lastly, and this is, I think, quite interesting, notice that the ambient dimension D doesn't really enter those bounds. I mean, in the average slice case, it just doesn't have any effect. Whereas in the max slice, it is rather the rank of the covariance matrix that appears as opposed to D itself. Now, well, if sigma is full rank, then K equals D, but generally K can be even smaller, which I think is kind of an interesting observation here. And let me maybe say a couple of words of how we establish those bounds. Well, for the average sliced case, we strongly rely on the one-dimensional empirical convergence rate analysis due to Bobkov and Ledoux. And specifically, we showed that if mu is log concave, then all of its projections are log concave as well. And this allows us to control from below the Cheeger constant associated with these projected distributions. Now, if you're not familiar, the Cheeger constant is essentially a measure of how bottlenecked a certain distribution is, and it becomes smaller the more severe are the bottlenecks that present, like in this small cartoon example that I have over here. But the point is that under low concavity, you can control Cheeger constants from below, which gives us this uniform in theta upper bound on the empirical convergence rate that is associated with each of these projected distributions. And obviously, this supremum over here is an upper bound on the expected average slice distance. And then using Bobkov and Ledoux, we can further upper bound the entire thing by the right-hand side that appears over here. Okay, so that's the average slice case. Now, for the max sliced bound, there's some extra work that is required. Essentially, you want to transform this expectation of a supremum into a supremum of expectations, which you already know how to bound. And this involves certain covering arguments of the unit sphere together again with concentration inequalities for Lipschitz functions. And this is where these two extra terms in the second bound really come from. Okay, so that's pretty much for empirical convergence. And the key takeaway message here is, again, no curse of dimensionality. You get nice rates. Constant may depend on some notion of dimension. But other than that, dependence on n is dimension free. And what's interesting here is that it turns out that under the slice framework, we can do much, much more than this in our statistical analysis, going far beyond what is known and possible at the moment for the classic optimal transport framework, which more specifically, we can characterize distributional limits of empirical estimates. And maybe before I talk about this, just to understand how much detail I should get into, how much more time do I have?
So we have about 8 minutes.
8 minutes. Okay. I mean, I think I can cover this in 8 minutes. So, right. So, like I said, we can characterize distributional limits, and these are very important for through principled or valid statistical inference because they allow us to derive confidence intervals on our estimate. They allow us to derive efficiency bounds on empirical estimates. They allow us to derive consistent resampling methods, and all of these are very nice to have. I mean, you're in the business of kind of statistical analysis. Plus, limit theorems for slice WP were mentioned in some past works, but remained unproven. And I think, I mean, this is an interesting open question that is worth some attention. So let's talk about that. Now, to fill this gap, we have recently essentially developed a general methodology for establishing limit theorems for regularized optimal transport distances that relies on this notion of the extended functional delta method. And I mean, in spirit, this is very similar to the classic delta method that accounts for convergence of functions of convergent sequences of random variables. And I should say that, you know, the general approach that we have in the paper is much broader than just sliced distances. We can use it to treat entropic and smooth optimal transport as well. But I will present some simplified, sort of adapted version just to make it slightly more digestible. All right, so let's see how we can do that. And with this, I mean, let me try to explain how this result works. Okay, so say you have a class F, script F of Borel functions, and essentially this script F class will in a moment become the function class in our dual form. All right. Now, let me define this L infinity of F as the space of all bounded functionals from the class F to R, and I want to equip it with the sup norm as defined over here. And in this context, I want to think of probability measures, probability distributions as elements of this L infinity class with this notation of mu operating on F simply denoting or representing the expectation of F with respect to mu. Okay, that's basically kind of a standard Riesz representation theorem. But the point is, think of this as a superset of the space of distributions. Okay. And then lastly, I want to consider a functional, call it cap phi, that maps distributions, or more generally, from L infinity to the real line, which we will soon cast as our slice WP distance. And this is basically the setup. Now, under this setup, I need three ingredients. I need to fulfill three assumptions. The first of which is, if we can show that the scaled empirical process that is indexed by this function class converges uniformly to some limiting element, call it G sub mu, in this L infinity space. This is essentially a uniform CLT kind of statement. That's ingredient one. Then we need to show that our functional is in fact Lipschitz in the sup norm that I've just defined. And then lastly, characterize what's known as the Gateau directional derivative of our functional at the centering point mu. And this essentially corresponds to some perturbation style analysis of phi. You perturb the input by a little bit. You ask, well, how much does the value of the functional changes at this 1/t time scale? And if we have these three ingredients, then under these conditions, we can deduce that applying phi, the functional, to our sequence of empirical measures, the following convergence in distribution holds, with the limiting variable characterized as this directional derivative, this Gateau directional derivative at the centering point, evaluated at the limiting element G mu. Okay, so that's the result. And I mean, I know that it's not super easy to understand seeing this for the first time. And don't really worry about it, because the main takeaway that I want you guys to have here is that we have this generic tool that under certain technical conditions will enable you to derive distributional limits for functionals of empirical processes, which is a structure that often comes up in statistical optimal transport and more generally in statistical learning theory. Okay, so that is out there, and just check out the paper if you want to know more about this general framework. But let me show you how we apply it to get a limit theorem, for example, for average slice WP. Okay, so specifically, I want to consider this so-called one sample alternative setting where mu is fixed, mu is approximated from samples by this empirical measure, and the population distributions are different. This is why we call it the alternative hypothesis. And further, let me assume that P is greater than 1 because there's a slightly different, a bit more general argument that I can use for the P equals 1 case. Now, the goal here is to cast this question under the general framework. So let me define my functional phi of eta, eta being the variable, a probability distribution, which is my variable, as the average slice WP distance between this eta variable and my fixed nu raised to the power of P. This is my functional. I want a limit theorem for this guy, right? Now, the first thing that I need to do, and I can, under the assumption of compact support, indeed do that, is show that this functional is Lipschitz, and I can show, in particular, show that it's Lipschitz in this max slice W1 distance, which is great because it exactly corresponds to the structure of a soup norm with respect to an appropriate function class. And where is this coming from? I mean, just recall the duality. If you look at the dual form for this max slice W1 distance, then you realize, oh, exactly, I have a soup norm here with respect to a function class that composes this Lipschitz-1 functions with these projection operators. Okay, so I have my Lipschitzness. I have my Lipschitzness of the functional, and this is a gradient number one.
Sorry, it is Lipschitz with respect to what?
With respect to this norm.
Okay.
Right. So if you look at basically phi at eta 1 minus phi at eta 2 absolute value, you can control it by the soup norm of eta 1 minus eta 2.
Okay. Do you need to take a square root of p, or you don't need?
Sorry.
It's a p's power of the slice.
Yes, so I'm using p's power now. In a minute, I'll tell you how to remove this p's power and get just a limit theorem.
Okay.
The p's power is not consequential.
Okay.
All right. I mean, on compact domains, you can understand if the original one, right, is Lipschitz, then also the p's power. Yeah. So that's ingredient number one. Ingredient number two, we want our uniform CLT, right? And I mean, indeed, we can verify that the empirical process that is indexed by this function class converges uniformly, which we can do using standard kind of tools from empirical process theory. Essentially, this comes from the fact that Lipschitz-1 functions over the real line form a so-called mu-Donsker class for which the uniform CLT holds, and composing these Lipschitz-1 functions with these projections, which is a parametric function class, does not really affect this Donskerness. So you still have this uniform CLT holding, and that's our second ingredient. And with that, I mean, the last thing that remains is to evaluate the directional Gateau derivative of our functional at the centering point at mu, which is, like I said, essentially a perturbation analysis at this linear time scale. And you can indeed do that and show that the derivative exists, and in fact is given by this expression over here, where the lowercase phi sub theta that you see inside the integral is essentially the optimal dual potential from the projected mu distribution to the projected nu. So it's kind of interesting, but this optimal potential appears in the derivative. And also maybe let me mention that this derivative turns out to be linear in its variable, this rho in the direction over here, which is important for a reason that I will mention in a second. But I mean, this basically gives me everything that I need in order to apply the general theorem, which yields the following limit distribution results, which essentially gives me asymptotic normality of this empirical average slice WP distance with the limiting variable characterized by this formula, which comes from the derivative expression that we've seen on the previous slide. Okay, and this is the last thing that maybe I'll spend 2 minutes here and I'll wrap up. Now, a few things to say here. First of all, like I mentioned before, the methodology is broader than just this one result. In particular, we can extend this to max slice distances. We can treat the p=1 case. But beyond that, first thing that I want to mention here that I think is slightly more important is that this linearity of the Gateau derivative that I've said and kind of alluded to before, in fact, automatically gives us consistency of the bootstrap, which gives us a computationally tractable way for estimating this limiting variable or its variance for that matter. I mean, you know the variance, you know the variable in this situation. This is good to have because otherwise, I mean, how do you kind of figure out this quantity that depends on the population distributions? Then, second of all, if you don't like the p's power, and this is back to your question from before, right? Then you can easily remove it just by applying the standard delta method for the pth root function to this theorem over here, right? So the asymptotic variance will change somehow in relation to the derivative of this function, but I mean, the result will qualitatively remain the same. And lastly, in the paper, like I also said before, we have similar theorems for entropic optimal transport, smooth optimal transport, which all comes from this general framework. So again, if this is interesting to you, do check the paper out. And maybe with that, let me, this is all I was planning to cover. So if we have another minute, I can conclude.
Sounds good. Yep.
Yeah. All right. So, I mean, let me start from this classic WP, right? Like we said, defines this beautiful and rich metric on the space of probability distributions. And while these distances are very popular in practice and enjoyed some excellent empirical success, they do suffer from statistical and computational hardness issues in high dimensional settings, which is a major issue for trying to kind of couple these applications with the meaningful and useful theory. And to deal with that, we've discussed this approach of slicing, where essentially we project distributions down to lower dimensions and then either average or maximize over the different projected distances. And we've seen that sliced optimal transport or sliced Wasserstein distances retain the metric and topological Wasserstein structure. They retain the duality, but not quite serve as a proxy of the classic framework. We've seen that they are easy to compute subject to formal accuracy guarantees. And we've seen that we can devise a rich statistical theory for them, encompassing empirical convergence rates, limit distributions, and a bunch of other things that you can now use for valid statistical learning and inference. So, I mean, I think all in all, it's kind of fair to say that slicing is a rather satisfactory regularization method for optimal transport that nicely balances out the different aspects that we care about. And these are two papers that I've mainly referred to throughout this talk. They contain, I think, almost all the results that I've mentioned. I apologize. I was planning to have an archive link for this guy by the talk, but we posted this late Friday, and so we don't have a link yet. Just check out my website if you want. I mean, I will have a link there by the end of the day. And yeah, with that, guys, thank you so much for listening. I'm sorry for going over time a little bit. I would be happy to take any questions if you have.
Thank you so much. Let's thank our speaker first. Thank you, Ziv. This was a fantastic talk. So let's see if there are any questions. And have in mind that we only have 10 minutes for questions. Ziv has a hard stop at 1:30 our time. So
yeah, I gotta go teach. So I apologize for that. Yeah, Daniel, you wanted to ask anything, or was this a leftover hand from before?
No, it was a leftover hand, but
okay.
Thank you for a great talk. That was a lot to dig through, a lot to eat. Yeah.
Yeah, I know. I'm sorry if it was too much.
No, it's a good thing.
Yeah.
So the video will be available. Somebody's asking, I think Ikun is asking if it's possible to have the presentation. I mean, the video is going to be there, but that's up to.
Okay.
Sure, I don't mind. I can. Should I send it to you, Sohail?
Sure. Yeah, and I share it with anyone who is interested. I put the link.
Yeah, no problem.
Okay. Any technical questions?
I'm just wondering if this technique can be applied from the log concave to the general sub-Gaussian something.
So which technique?
The
functional delta method, or
yeah.
This one?
Yeah.
Yeah, so this does not assume local cavity. Local cavity we only assume for getting these nice empirical convergence rates. And I mean, the reason we really assumed lock concavity for deriving empirical convergence rates is because we wanted to use some nice results that Bobkov and Ledoux had, right? Because I mean, this, right, you can always upper bound this guy by this guy, just taking a supremum inside the integral, right? So that there's nothing here. But the point is, how do you control empirical convergence uniformly over theta of all these projected distributions? And turns out this is kind of, at least chronologically, the way we arrive at this result, that if you can control uniformly from below Cheeger constants, then you can get an upper bound uniformly in theta, right? And this comes from, and then the connection from Cheeger constants to lock concavity is kind of, it's almost standard. Yeah, so this is where it comes from. But, you know, if under some other assumption, you can get control over this guy, then you can replace lock concavity with this other assumption.
Right. So one piggybacking on this, right? Exactly at this point, right? This is when we do like classic slicing, or slices are actually the inner product with theta, right? Like, so it's a linear slicing. And we had this idea of generalized slice Wasserstein distance in Norif's 2019, right? So you can have a class of nonlinear functions that go from RD to R in general, and the linear case is a special case of that. And okay, so one good way of thinking about it is that if you can transform your space using a bijection, invertible function, a d-dimensional space to a d-dimensional another d-dimensional space, and do your slicing in the range of this bijection, right? Then that's still a distance you can show, and that's a special type of generalized slice distances. And I think this bijection could potentially help us make the distributions become log concave. I'm just thinking out loud, right? Like, but we need to maybe.
So, do I understand correctly? You're like kind of thinking of a feature map that will put us in some other high dimensional space, and this other high dimensional space we can just use linear slicing.
Right. So this composition of that bijection and the linear slices becomes a nonlinear slicing, right? And you can show that this still gives us a distance between distributions.
Right. So that's interesting. The question is, what is the class of distributions, and what kind of functions can you use on a corresponding class that would take the original class, which was presumably not lock concave, and now make it into a lock concave one?
That's right.
I mean, it's an interesting question. I don't know the answer off the top of my head, but
maybe we should follow up.
Right.
I
agree with you that it might offer some extra flexibility in terms of the assumptions that I require here, because essentially you now don't quite need the lock concavity of the original thing. You just need to be able to transform it into a lock concave distribution. Yeah, I mean, I like the idea. That's something to think about.
Yeah, I'll reach out for some further thoughts maybe later.
Yeah, I'd love that for sure.
Any other questions?
Yeah, but let me maybe in the context of Yukun's question, this one over here does not need lock concavity.
Okay.
Yeah, so this is slightly more, I don't know, robust maybe.
Okay.
Yeah.
Okay.
I really like this one, by the way. I really enjoyed this, so I'm going to read the paper for sure.
Yeah,
Oh, sorry.
I think it's cool. I think it's useful, and the framework is pretty much. I mean, we tried to kind of, honestly, there's not a whole lot going on here in terms of. I mean, it really very strongly relies on this existing idea of extended functional delta method, but it may sometimes be kind of cumbersome to try and apply it to a specific problem. So we wanted to have a framework that is easier to apply in the context of regularized optimal transport. And so, I mean, if you kind of work out some intermediate steps, I think that what we have there is much closer to plug and play than trying to, start from the actual extended functional delta method and build towards the result that you are looking for. So yeah, I mean, I like this as well. I think it's quite nice.
Very nice. Other questions?
Could you go to the page to the central limit theorem of slice OT? I think maybe next page. No, next page.
No, I think that's my last.
No, I remember there one page you introduced the proof technique. Says one step will prove the f. The theta is one Lipschitz. So the step 2 and 3 is just classical result in some empirical process, right? The only you just need to prove if this function is
I mean, I am not familiar with this specific result being kind of already present in the literature, but yeah, this is a well-known fact that Lipschitz one functions in one dimension are a Donsker class. So for them, you have uniform CLT. Now, we still had to compose them with this projection, but this doesn't change the Donskerness. I mean, essentially, Donsker classes parametric classes are Donsker, so long that you have parameter bounds, which is, of course, the situation here. So yeah, 2 is kind of standard here. This is just empirical process theory. 3, this is something that we had to do, but it's also not very difficult, right? You essentially look at WP to the P in this case. And by the way, if you're wondering why WP to the P as opposed to WP to begin with without the Pth power, well, because we want to be able to use duality. Duality is the key ingredient that sits behind everything that is going on here. And the dual form applies not to the Wasserstein distance, but rather to the Pth power of the Wasserstein distance, which is when you get back to the linear program. Yeah, and once you look at that, I mean, you just kind of, analyze differences of WP of mu plus a perturbation minus WP of mu versus just mu without the perturbation. And you can, show by essentially upper and lower bound that this is the quantity up to this, again, up to little o of t terms, that this is the quantity that dominates this difference. Yeah.
Great. Fantastic. Ziv, we don't want you to be late to your class. Thank you again for this wonderful talk. Everybody, if you unmute and we thank our speaker one more time, I appreciate that.
Thank you, guys. It was really fun. Thank you for all the interesting questions. If you have anything come up, offline, feel free to shoot me an email. Happy to talk, happy to discuss.
Awesome. Great. Thank you again. Talk to you later.
All right. Looking forward. Take care.